So modern atomic theory is the idea that all matter is composed of atoms. And it grew out of observations and laws. Observations and laws say, this is what happens. Doesn't try to explain why. The theory is explaining why. And so the three laws that were important are law of conservation of mass, law of definite proportions, and law of multiple proportions. So we'll look at those. So we've already talked about Antoine Lavoisier, and he came up with the law of conservation of mass. In a chemical reaction, matter is neither created nor destroyed. So the idea here is whatever your things that are reacting are, we call those reactants, they have a mass. And when a chemical reaction occurs, the atoms that compose those reactants are just rearranging, like taking apart a Lego structure and building something different, using all the same bricks. And at the end, the mass of the products is the same. That makes sense? No bricks or atoms are destroyed, or created for that matter. Here's an illustration. Sodium and chlorine will undergo a chemical reaction to form sodium chloride. If we mix 7.7 grams of sodium with 11.9 grams of chlorine, we end up with 19.6 grams of sodium chloride. 7.7 plus 11.9 is 19.6. The mass of what you start with is equal to the mass of what you end up with. The particles that were in this original sample are now in here. The particles of chlorine that were in here are now in the salt crystals, and they've just rearranged themselves. On worksheet 2, there are some questions about these laws, and students tend to make them more complicated. So I have not taught you anything about molar mass or molecular weight or stoichiometry or even what a chemical reaction is. So on that worksheet that we'll work on Thursday, we're not going to do anything like this. This is just adding, really. If you add the reactants, their mass has to equal the products. And so those problems are solved just by adding and subtracting. Let's think about this. When a log completely burns in a campfire, the mass of the ash is much less than the mass of the log. What happens to the matter that composed the log? A, the matter that composed the log reacts to form gases that are released into the air, or that matter is converted into energy, or the matter is still present in the ashes but has a much lower mass.
A.
It's A. Law of conservation of mass says we can't change that matter into energy in a chemical reaction. And the mass just can't change. The mass stays the same. So the reason that the ashes weigh so much less is because most of what composed the log, combined with oxygen, formed H2O and CO2, which are gases, and they float away. And that's why Lavoisier did his experiments on burning things in a closed container, because then those gases didn't float away. Law of definite proportions tells us that all samples of a given compound, regardless of where they came from or how you made them, have the same proportions of their constituent elements. And Joseph Proust, a French chemist, came up with this. So as an example, if we take 18 grams of water and decompose it into its elements, we'll get 16 grams of oxygen and 2 grams of hydrogen. So we can look at the ratio, the proportion of those elements by their masses. So 16 grams of oxygen to 2 grams of hydrogen gives us a ratio of 8:1. 8 grams of oxygen for every 1 gram of hydrogen. So let's apply that. The mass ratio of nitrogen to hydrogen in ammonia is 4.7:1. If a sample of ammonia has 10 grams of hydrogen in it, how many grams of nitrogen does it contain? So that ratio, 4.7 grams of nitrogen per 1 gram of hydrogen. The sample we're looking at has 10 grams of hydrogen, but the ratio needs to be the same. So if we want this value to be the same and the denominator got multiplied by 10, what do we have to do to the numerator? Also multiply the numerator by 10, right? So 47 grams of nitrogen. 4.7 to 1 is the same as 47 to 10. That make sense? So this ratio, so letter D, the ratio is constant. It doesn't matter where you got the sample. Okay. Any questions? Another example. 2 samples of carbon monoxide are decomposed into their constituent elements. One sample produces 17.2 grams of oxygen and 12.9 grams of carbon. The other produces 10.5 grams of oxygen and 7.88 grams of carbon. Show that these results are consistent with the law of definite proportions. So law of definite proportions says that the ratio, if the ratio is 17.2 grams of oxygen per 12.9 grams of carbon, that ratio should be the same as the ratio of 10.5 to 7.88. Now, we can't just tell that by looking at it. So our first sample, 17.2 grams of oxygen to 12.9 grams of carbon. So we can simplify that fraction, 17.2 divided by 12.9 gives me 1.33. Should have 3 sig figs. Grams divided by grams cancels out. This is a ratio, it has no units. Then if we look at the other one, 10.5 grams for every 7.88 grams. Now this one gave me on the calculator 1.33 repeating. This one is a little bit different. It's 1.33248731. But using sig fig rules, this should also have 3 significant figures and the ratios are the same. If we know the ratio for a compound and we know the mass of one of the elements in a different sample of that compound, let's say we were looking for, we had a sample that had 7.88 grams of carbon and we wanted to know how much oxygen there was. Well, we can put a variable in there, x, and we know the ratio is 1.33, and so we can find the mass of that other element. The law of multiple proportions, when you get down to it, it makes sense, but when you're trying to explain it, it's just a lot of word salad. So when 2 elements, call them A and B, form 2 different compounds, the masses of element B that combine with 1 gram of element A can be expressed as a ratio of small whole numbers. That just doesn't seem to make a lot of sense. This was published by John Dalton in 1804. What's going on here is because atoms are indivisible particles, when they combine to form a compound, you're going to have small whole number ratios of atoms. So if you have 1 atom of A, it can combine with 1 atom of B, or 2, or 3, or 5, or 6, but it could not combine with 1.2 atoms, right? So what this is saying is you have 2 different compounds, same element. Do the ratio of elements like we did for definite proportions. They're going to be different because they are 2 different compounds. But if you take the ratio of the ratios, you get a whole number, which just seems like some math trick. So let's look at this. Carbon monoxide and carbon dioxide. They're both formed of carbon and oxygen, but they're different compounds. This has 2 atoms of oxygen for every 1 carbon, and this has 1 atom of oxygen for every 1 carbon. So the mass ratio of oxygen to carbon in carbon dioxide is 2.67, and the mass ratio for carbon monoxide is 1.33. That's what we just calculated in the previous example. If we take the ratio of the ratios, take the larger one, divide by the smaller one, we get 2. Because there's twice as much oxygen per carbon in the carbon dioxide compared to the carbon monoxide. Any questions? Hydrogen and oxygen form both water and hydrogen peroxide. So the decomposition of a sample of water forms 0.125 grams of hydrogen to every 1 gram of oxygen. The decomposition of a sample of hydrogen peroxide forms 0.0625 grams of hydrogen to every 1 gram of oxygen. Show that these results are consistent with the law of multiple proportions. Here's a question on worksheet 2. It's pretty similar to this. So we have the compound water. So we've got 0.125 grams of hydrogen to 1 gram of oxygen. 0.125 grams of hydrogen to 1 gram of oxygen. So that would be a ratio of 0.125. And then we have hydrogen peroxide. And that has a ratio of 0.0625 grams of hydrogen for every 1 gram of oxygen. And you do that and you get 0.0625. These ratios are not the same because water and hydrogen peroxide are different compounds. Their formulas aren't the same. They're different compounds, different properties. But they're both composed of just hydrogen and oxygen. So if we take the ratio of these ratios, we should get a whole number. If you want the whole number, you have to take the bigger one and divide by the smaller one. So the bigger one is 0.125, and we're going to divide by 0.0625, and what do we get? Okay, I'll do it. 2. Water is H2O, hydrogen peroxide is H2O2. So this has 1 hydrogen for each oxygen. This has 2 hydrogens for each oxygen. And that's why this ratio is twice as big as that one. They observed these proportion laws before they really determined that atoms existed. And it supported the idea that atoms existed. Any questions? So, John Dalton explained those laws with his atomic theory, and it has these 4 points. Each element is composed of tiny indestructible particles called atoms. All atoms of a given element have the same mass and other properties that distinguish them from the atoms of other elements. Atoms combine in simple whole number ratios to form compounds. Atoms of one element cannot change into atoms of another element. In a chemical reaction, atoms only change the way that they are bound together with other atoms. So we now have overwhelming evidence that atoms are real. But this was a big deal in 1808. This is an example of how theories sometimes need to change when we get new information. So these statements were all true as far as they knew at the time. Are atoms truly indestructible? No. Atoms can be smashed. And those involve nuclear reactions. So in chemical reactions, they are indestructible, but not in nuclear reactions. All atoms of a given element have the same mass. Is that true? Remember hearing about isotopes? We'll learn a little bit more about that. So this is also not quite true. Here, with that qualification, in a chemical reaction, this is true. But in nuclear reactions, elements can change from one element into another element. So new information comes up. We don't just throw the whole theory out. We modify it to agree with past and current information.